Hello community, today we have something special. We look now at in-context learning visual prompt structure. And yes, we are talking about multimodal foundation models, and we will test out the latest and greatest vision language model. You remember in my other videos I showed you here that we can use in-context learning plus, and the plus indicates here a context length of more than 1 million token. And for text only, we said, hey, can ICL Plus substitute all the fine-tuning that we do with our LLMs? Is there cheaper, faster methodology? And for text, we found it. But now we have to answer this question for vision language model. So let's start. Now, you might say, hey, wait a second. In your last video, you showed us here the exact code how to fine-tune here a vision language model with free collabs and everything, and jags and flags and pie trees and everything. Yes, but look, we just looked here at Polygamma from Google, a 3 billion free trainable parameter model, so a tiny little VLM. And yes, after 15 minutes, after 13 minutes, we had some beautiful description, and the system absolutely understood what it saw and could give us here a textual description of the visual content. And we've done this, and it works beautifully on very small models. But now we go to exact the opposite of our spectrum. We go to the trillion free trainable parameter size models. And we want to see, are they powerful enough that we don't have to fine-tune them anymore? And to give us here all the data and all the insight we have here from Stanford University, and yes, from Andrew supervised here this study, we have a new study, May 16, 2024, about many-shot in-context learning in multimodal foundation model. And this is a beautiful study. And if you see the wording MMFM, now you know it, multimodal foundation models, beautiful. Now what we need dataset and models. So we start with 10 dataset. Stanford starts with 10 datasets on clinical photos of skin disease, on eye disease classification, on chest X-ray images, on pathological images, on camera images, satellite images. You get the idea. And we have hundreds and thousands of images. This is how it looks. Skin, eye, X-ray. Yes, pathological images. Great, great, great. And we need models. We test models. And we go here for 4 models. The latest GPT-4 Omni, the GPT-4 Vision Turbo, not so great yet, the Gemini 1.5 Pro with 1 million token context length, and Claude 3 Opus. Now, Stanford noticed, testing those systems, that Opus currently only accepts up to 20 images in one request. And yeah, if you go for hundreds and thousands of images, if you really fill up here the maximum context length, 20 images is simply not enough to be a contender. So Stanford crossed out Claude 3 Opus because it's just not powerful enough. Yes, I know, community, it really hurts. Well, the same happens to GPT-4 Vision Turbo because Omni is so much better that they said, hey, listen, we don't have to test for Vision Turbo. We have the best, the latest, the greatest Omni. So let's go with Omni and 1.5 Pro. So those are our 2 models. We focus now on many-shot in-context learning with extreme scaling here, where we have a query image and we have within our prompt multiple 100,000 of images as demonstration examples. Later on, we have even a much more beautiful version. But let's start here. So those are the results. In green, you have GPT-4, and in blue, you have Gemini. Well, you see here, if you look at the bold results, this is just one parameter of efficiency, never mind whatever it is. But Gemini 1.5, yeah, he is winning here this comparison. But that's not so important. Much more interesting is here the exact behavior of the system. And one sentence was, hey, out of this 10 data set, the Gemini 1.5 Pro performance continues to still improve, to go up to the highest number of demonstrating example in a prompt. Even we go up to 1000 visions. and the performance goes up. And I said, wow, this is interesting. So let's have a look at this now in detail. Here you have on the x-axis a log scale, and on the y-axis you have here the accuracy. I think it's all over the F1 score, so particular benchmark data. But what's interesting, in blue we have Gemini, and in green we have Omni. Now let's look at blue first. You see here, and this 1, 2, 3, 4, 5 blue marked examples. The more examples we put in, the better the accuracy becomes. So the more many-shot demonstration example we provide within one prompt, the system learns and learns and gets better and better and better. Sometimes it is linear but almost saturated, like here. The blue one, yes, goes up and up, a little bit tiny up. Or here, yes, it continues to go up here to the maximum number of examples the prompt can take. And this is why we say we have a log linear dependency here of the system. You see, this is almost linear here of the blue. But we also have, from these 10, 5 that are not performing in this way. Look here at the drug OD. We go up, then we plateau here with a number of training examples here in our prompt ICL. Then we go down, and then it continues to go up. So this is an interesting behavior that we encounter here. Or we start slow, then it increases significantly, and then we plateau out. So this is a very interesting example. What's happening in the internal dynamic and why this is happening. If we look now in green to GPT-4 Omni, you see also substantial performance improvement in the green line here, if we go up, but not as consistent as here, the blue lines. You see in green, sometimes we start with a 0-shot, real good, 90% accuracy, but then the system gets few shot examples, the system starts to learn, and it learns, and the performance goes down. But the more example we provide to the system, the more we move here to this direction, the better the performance gets. And even here, so classes here, the Gemini system. So this is an interesting system. Look, we have this multiple times on multiple data sets. And question is, of course, what's happening here? And one simple idea I personally have is look at the training data. You know, we have the pre-training data, the fine-tuning data, and the DPO alignment data. But if you look at the sheer amount of data, the pre-training data are dominant for the behavior of our LLM. Whatever we do, we have then a pre-trained vision language model or a large language model. Now, we do not know exactly the pre-training data of Gemini or of OpenAI because it's proprietary AI. So, you know, there are lawsuits and everything and whatever. Who is suing who? I don't know. I don't want to care. But unfortunately, let's assume that we have different pre-training data from Google and from OpenAI. I think this would explain here some differences here in the performance scheme. But let's forget about this for a moment. Okay, Gemini is better here, has a better pre-training set here for the visual systems. But in general, you can see the tendency is up. The tendency is, hey, give us more many-shot examples and the performance of the system will go up close to 100% for this example. Or it will fluctuate somewhere, but in general, the tendency is it works. And this is the important fact here in this. So, main insight of this study from Stanford University, both models benefit substantially from many-shot in-context learning examples. And if it's not optimizing at the max, you have an optimal demo set size where it plateaus out. For Gemini 1.5 Pro, we have this log linear performance up to the maximum number of examples we can put into a prompt, 1,000 plus images. And the performance continues to improve significantly. But as I told you, GPT-4 Omni, it is less stable compared to Pro, and the performance is varying significantly as the number of the example increase, and we have this V-shape suddenly when the pre-training performance does not meet here the new domain data. For Pro, let me be very specific. We have Gemini 1.5 Pro and Gemini 1.5 Pro that only are published a different month. So I'm talking here about the May 2024 version with 1 million token context length. Yes, there's also upcoming now the Gemini 1.5 Pro with 2 million token context length. But this study is here particular about this system. And look, hey, we have a new Gemini 1.5 Flash, which has also a real beautiful performance. It should be significantly faster. The complete code base for all of this study is available at github.com, Stanford ML Group, Many in Context Learning. Have a look, it's interesting. But you know what's the really fascinating part of this story? They also looked at batched many-shot in context learning plus. So what does it mean? We do now multitasking in one prompt. We do not have one query at the end of our examples, but we have multiple queries to ask our vision language model. Is it possible to do this? Or is it just that the first one is right and the rest is all nothing? Or is it that it goes down linearly the more queries we have? Or it's not happening at all? Does it stay constant? Does it even increase the quality the more queries we have? This was an interesting question, and Stanford looked at this and found an answer. So the impact of batching queries together. So now this is it's a little bit more complex. So let's start. So we have a large set of demo examples in our in-context learning. In the prompt leads to much longer sequence length, 1 million plus. And therefore we have higher inference time and costs. But if we consider batching now the queries in a single prompt together to reduce the per query cost and examine the impact of different batch sizes on the model performance, does this help us? Does this work? Is this possible to implement? And the amazing answer is yes. Look here at the results. Our thin line here gives us the zero-shot experience. When we add more queries here, x-axis, we add more queries to a single prompt. And here the full line is here with our Gemini 1.5 Pro many-shot batching. So you see, both systems work. Look at this. Even if you put more queries in a prompt, the overall system performance, I would say, stays almost the same. Some variation, stays almost the same. Look, even gets better here in this case. So this is now amazing, this in-context learning mechanism. It is not just that it can focus only on one query, but we can batch the queries together, have multiple queries, ask here in just one prompt. So this reduces the cost significantly. And Stanford looked at this in detail. So at first we have no substantial drop in performance if we do the batching of our queries, which is amazing. It's great. It shows us how powerful in-context learning is. But if we look at the costs, so what we have at first, since we use many-shot in-context learning and we do not touch here the weight tensors of our vision language model, so we do not fine-tune at all, we have zero additional fine-tuning costs. We just run with a pre-trained system and we have an in-context learning. That's all we have. But of course, the per query inference now, since it's huge, can be costly and slow because we have long input context, 1 million, 2 million token. So how does it balance it out, the cost and the latency? Stanford said, first we look at the zero-shot regime. So we see a substantial, per example, latency reduction due to query batching. Well, of course, if the system works and we put more queries together, and they examined this in detail in two datasets. You see the first dataset, they had a 10 times reduction in the latency, and in the second they had a 2-time reduction in the latency. And for the costs, they are similar because, yeah, of course. However, if they now look at the many-shot regime, they observe substantial reduction in both the per example latency and the per example cost. So for the dataset, the particular numbers are, there is a 35%, no, stop, there is 35 times a reduction in the latency and a 10 times reduction in the costs for this particular dataset if you have the many-shot regime. And for the other dataset, there's a 20 times reduction in the latency and a 45 times reduction in cost. Now, this is significant. This is exactly what we need to be faster, better, and cheaper. Isn't this fascinating? If you want to have the exact number, here they are. So what is now our final insight? What does Andrew tell us about this study? What does Stanford tells us? Fine-tuning our open source model is the standard practice when coders have access to some data sets, but many-shot ICL, and we talked here about 1 million plus, so ICL plus, may remove the need for fine-tuning our system, making it much easier to develop customized approaches. Hearing this from Stanford University, this is now something special, especially not only in a large language model, only text, but now in a vision language model. So they tell us, hey, fine-tuning is beautiful, but today we know, May 16, that many-shot in-context learning with a huge context size may remove the need for fine-tuning because we have something that is maybe better, maybe at least as good as fine-tuning. And we do not have to pay as much for the proprietary system that we are allowed to fine-tune them, like OpenAI or Gemini. Now, I think this is fascinating. And this closes here my mini-series I started weeks ago with pre-training LLMs, ICL plus, RAG system. The latest one was here, in-context learning outperforms for text only, please. Fine-tuning and RAG. When we go to extreme scaling, and today we looked at our big monster system, GPT-4 Omni and Gemini 1.5 Pro, and we see that this trend continues, that ICL performs. It is amazing. Please have a look at this study, read it yourself, get familiar with even more details, and maybe you will be convinced that we have now a second pillar, a second strong opportunity, not just to fine-tune our models, but also here to have a many-shot in-context learning with this huge prompt size that we have now in the new multimodal foundation models. Remember, Gemini 1.5 Pro, 1 hour of video you can put into the system to be analyzed. I think this opens up new possibilities. And it would be great to see you in my next video. Now, if you listen to the end, sometimes I have a personal statement, my little personal thoughts. I imagine this pre-training to be extremely expensive. And I hesitated to touch this topic because I said I don't have the money, simply $100,000 plus $300,000. But think about it. If we have this opportunity now, and let's say we're designing an AI system for a hospital or a bank or insurance company, whatever you imagine, are we tricked into something? Now, GPT-4 Omni has to be a system for everything, for everybody on this planet. But if we design now special system for very specific tasks in a hospital, in a bank, where you can say, hey, I take all whatever my employees are doing. I see exactly, have all the training data. I know exactly what is their job. I know exactly what mathematical formula they use. I know exactly how they argue. I know exactly what are our products. I have all this data here from years and years. And what if you only train on those data? Because you know what? in those huge monster LLMs and vision language model, you know what we have? We have almost a complete knowledge of the internet. We have the history of the British Empire. We have all of French poetry. We have the complete British literature from the, 11th century on. We have everything about Hollywood, Bollywood, news and actors and whatever. We have everything about psychology. We have everything about the latest trend of K-pop. We have, especially in the US, there seems to be a focus here on presidential election coming up in the news cycle. And we have conspiracy theories on the internet you cannot even imagine. We have the complete history of the earth. We have everything about cooking, baking, everything about fashion. My goodness. And everything about celebrities, what they think, what they wear, where they are, who they meet and who they look like. You know what? We don't need all of this. We can cross out all of this. If we, as specialists, design here for a hospital, for a bank, don't make the mistake that you think you have to go as big as GPT-4. This is not the case. The intelligence lies here in the perfect pre-training data of your system. That you have the data cleaned, perfectly focused on your task, and you know what? Your pre-training data become that you can handle them. If you have a very special task that you focus from the very beginning, only for your hospital or your bank, you have laser-focused, precise data in your pre-training data set for your specific task, you can get an extreme fast performance of the system. It will be economically to pre-train. Maybe if you have a computer infrastructure, if you are an insurance or a bank, you can use your local computer infrastructure. You have maybe no dependency on your cloud provider. You can do it in-house, and you don't have to pay for a proprietary AI system that you are allowed to fine-tune their system on their machine, where you have to send over all your company data to them. I think this opens up complete new avenues for us to design AI system, to design laser-focused AI system for a particular task. Fast, great performance, economically to pre-train, and then we use in-context learning plus for those system to adapt to further evolving specific task structures. But this is just one of my ideas, what I'm currently thinking and trying out. If you have some feedback on this idea, I would appreciate your comment here in the description of this video. Otherwise, I would say, I hope it was informative. I hope you had some new ideas about this topic, and it would be great to see you in my next video.